This is E658 lecture 48. Yesterday we were looking at some aspects of continuous time delta sigma modulators, and we identified excess delay as one potential problem with such modulators. And we also found a solution to the problem, which is to add a direct path with a gain G, where G equals TD for a okay, and the intuition behind why you need to add a direct path was covered yesterday. And as I said towards the tail end of yesterday's class, the same problem will occur. I mean, this excess delay becomes an even more severe problem when you have high order loop filters. And the solution is definitely adding a direct path around the quantizer is part of the solution. As we go along, when we look at second order modulators, you will find that just adding a direct path is not enough. You need to actually fool around with the loop filter itself. Okay. All right. So let's look at some other problems that are likely to arise with a continuous time delta sigma modulator. I'm using the first order as an example simply because it's easy to understand, because there's just one integrate, right? And most of these problems and solutions will carry over to higher order modulators with some minor variations here and there. Okay, but the basic idea of what happens remains valid even for high order modulators. Now, implementation wise, how would you implement the first order loop? You have to have an integrator, right? So, and the integrator has to integrate the difference between what? The input and the quantized output. So, and what is the simplest integrator you know? An Opamp based integrator is one way of realizing an integrator, and we know that everything in the world is now fully differential. And for those of you who woken up just like Rip Van Winkle after 50 years, right, is when you have a fully differential system, the quantities that are of interest are not the absolute voltages but the differences between them. So in this differential op-amp, the output voltage is a large multiple times, the difference in the output voltages is a large multiple of the difference between the input voltages. And I guess all of you have also taken other classes or are taking analog IC design. In any case, in this course early on, I explained the need for common mode feedback in all these fully differential structures. So this is the integrator. How many inputs should the integrator have? Look at the block diagram and tell me. It is basically subtracting two signals and integrating the result. So if you want two inputs, this is a 2-input integrator, right? So this is let me say this is 1 ohm, 1 farad, and please remember the reason why I told you it makes sense to do everything at at some normalized sane frequency, which I have chosen to be 1 hertz. Okay. In fact, I made a mistake. So the omega naught of the integrator is 1. So this must be, the capacitors must be 1 over RC must be equal to 1 radian per second. So this is fine. I'm sorry. If I choose R to be 1, I choose C to be 1. All right. Now, for the time being, let's assume that there is no excess delay, so that I don't have to worry about this path for the time being. So, what is the output of the integrator? Let me call this VIP, VIM, I'll call this VIP, V, Q, the quantize, let me call the output anyway, we used to call it V. Oh, it's a problem. Let me call this quantizer output P, V quantizer output M. Alright. So, if all these resistors were 1 ohm as shown here, then the current flowing in through the integrating capacitance is nothing but is proportional, is actually VQP minus VIM. Okay, that's the current flowing into the top capacitor, and I hope all of you understand this, right? There's no magic here. It's quite straightforward. Alright. So the integrator is inverting, so the output here must be sampled. Okay. So which is the input to the quantizer was always denoted by Y. So which is the positive Y and which is the negative Y? The top is positive, that's correct. So VYP, VYM, alright. And this goes to our quantizer, which is, I've just done it as a simple box here, but you've gone through the pain of designing a 4-bit quantizer and running all the simulations, right? And the output of the quantizer can go to a DAC, alright. And please note that we'll come back to this when I discuss a couple of minor details about the quantizer. But for example, in the 4-bit quantizer that you designed in your assignment, the output of if you just took the comparator array, the output of the comparator array is nothing but what kind of code? It's a thermometer code, okay? And you can directly use that to go and, so what kind of DAC makes sense here? You can use a full thermometer DAC, alright, okay, and you can see that the complexity involved in a full thermometer DAC is very small, because typically the number of bits in the quantizer will be 3 or 4 or 2, or if it's 1, of course there is no big deal at all. Okay, so the quantizer will basically be the thermometer output of the flash directly driving a thermometer DAC, and in many cases the DAC happens to be a current steering DAC because of several advantages, and the output of the DAC is a current which is fed to the input node of the op-amp. Please note that by Thevenin's theorem, applying a voltage here through a resistor is equivalent to pushing a current directly into the virtual ground of the op-amp, alright, and and in shunt with a resistor, that resistor will be between ground and the virtual ground of the op-amp, which means that I don't have to have it in the first place. You understand? Okay, so let me just illustrate quickly now. Whatever. This is equivalent to this is the Thevenin-Norton transformation, correct? Okay, so if you look at the resistor there in the Norton equivalent, what is the voltage across the resistor? 0, because one end is real ground, the other end is virtual ground, so no current flows through it, so I don't need to have it in the first place. Okay, So this must be V by R. Okay, both of them are equivalent. You understand? So if you had a current steering DAC, then instead of having VQ and converting it into a current by using this resistor, I can actually inject the current directly into the virtual ground of the. Is that clear? Okay. So for the time being, of course, we continue to work with voltages. This is the VQP, VQ. All right. So the most common mistake made in let's say you have a working op-amp and you have a working quantizer. Can you guess the most common mistake made by that you're likely to make when you hook things up together? The sense of the feedback will be positive. Okay. So instead of so how do you make sure that the feedback is negative? You go through the same old stuff that we've been doing for 4 years now, right? You break the loop at some point. Okay. You anchor put a differential voltage here. This quantizer has a characteristic like this. So if this input difference increases, this increases. If this difference increases, this is an inverting amplifier. So this difference must actually decrease. So you see that there is negative feedback. Okay. So that is that is one very, very common thing that happens. And see, these are all sample data systems. So it's not like you can do an operating point and figure out that you have made a mistake. Okay. I mean, so all right. So you run a transient and you'll find that the stuff just gets stuck at the maximum level of the quantizer. That's how you learn that you made a mistake in the sample. Does it make sense? Okay. Now, what do you think are what all problems do you think can occur with what all practical issues do you think can occur with the circuit? Of course, one could be the quantizer is not working properly, and but by now you know how to design the quantizer and make it work. All right. Okay. So this is a done deal. That's the assumption. The next thing is that the op-amp can be, apart from the quantizer, there is basically the resistors, the capacitors, and the op-amp. One thing we have to see is what happens if the op-amp is non-ideal. You understand? So the other thing is the resistors and the capacitors could be off from their nominal values. You think you have 1 ohm, but you know what perhaps you got is 1.5 ohms. Who knows? Okay. So the various things to worry about are: 1, RC time constant variations; 2, all right, and of course, just for completeness, quantizer non-ideal. Okay. So RC time constant variation. Let's attack the first guy. Try to understand what the problem is. Okay. Please recall that on an integrated circuit, if you make 100 resistors, all the 100 resistors will almost be equal. However, they'll all be off from what you intended to make by some random number, right? Typically, the fab tries to bound it to plus minus 20% or so if you're lucky. Sometimes it will go over a factor of 4, in which case you have to make sure that your design is robust enough, okay, or you do have some adjustment to bring the resistors back to some reasonable value close to what you want. You understand? But the bottom line is that all resistors and all caps change by the same factor on an IC. In other words, if you make 100 resistors, all that it means is that if the resistors could all be lousy, but they'll all be equally lousy. So such variations are what are called systematic variations. All right. Okay. So now, can you tell me what happens when all RCs, when all the R's increase? Capacitors are all ideal and equal to 1. Let's say all resistors increase by some factor. I don't know. Let me call this that factor K. In other words, instead of these guys being 1, they all become K. Yes, the gain of the integrator changes. In other words, in this block diagram, what happens? What is this equivalent to? If all resistors increase, the integrator is getting slower or faster? Slower, because 1 over RC, R is increased to K. So what happens to, instead of this being 1 over S, it becomes one over Ks. Okay. What do you think will happen to the DAC pulse width? The pulse width should remain the same. Okay, because the DAC pulse width is only governed by the clock width. The clock frequency is not changed, mind you, only the R's and C's have changed. So what is happening is that this 1 over Ks what was intended to be 1 over K has become 1 over, 1 over S has become 1 over K. So the first question is what happens to the NTF? Alright. In the first order case, it's very simple to understand. What do you think happens? As you know, you guys pointed out, it's like having a gain 1 over K, extra gain 1 over K in the loop. Correct? The sampled response of the loop filter or the loop gain, which was originally Z inverse by Z inverse by 1 minus Z inverse. Now, just multiplied by a factor of 1 over K. So, what happens to the NTF of Z? Is 1 by 1 plus Z inverse by K times 1 minus Z inverse, which is K times 1 minus Z inverse divided by K, what is this now? K plus 1 no, it is no K plus 1, it's just K minus KZ inverse plus KZ inverse, so it's basically K plus 1 minus K times. This is fine? Alright. Couple of things to notice. First, does this screw up your in-band NTF gain? At Z equal to 1, what happens? At small frequencies it is Z is equal to 1, that's correct. Hey, something is fishy. How is that possible? I made a mistake somewhere. Let me see. Oops. Alright, so around omega equal to 0, NTF of e to the j omega is basically k times 1 minus e to the minus j omega divided by k plus 1 minus k times e to the minus j omega, which is approximately k times. So the modulus of this is what I am interested in. It simply becomes k omega divided by k plus 1 minus k, which is simply e to the j omega is k times omega. Does this make sense? I mean, okay, it makes sense from the math, but physically can you explain this? Yes, that is the restatement of what I am saying. Yes, that's correct.
So the integration will become q to t.
Yes. Okay, please note that very simplistically I have reduced the gain, the DC loop gain by a fact. At low frequencies the loop gain has gone down by a factor of k, correct? And what is the NTF at low frequencies? It's 1 by loop gain, correct? So if the loop gain has gone down by a factor k, alright, the NTF must, the in-band gain of the NTF must go up by the same factor. That's what we are seeing, okay? Earlier when k was 1, the modulus of the NTF at low frequencies would simply be omega. Now it is k times omega, because the loop filter is less effective now at low frequencies. Does it make sense? Okay, so if I plot the NTF, let me plot this in dB. This is a linear scale, goes from omega is 0 to pi, alright. So the original NTF would have been something like this. All right. Now the new NTF is this is 0 dB, mind you. What should this be then? This is modulus of the NTF in dB. So this is 20 log to the base 10 of NTF. So what should this be? The out of band gain of his first order NTF is basically 6 dB. Correct? So this is for RC equal to 1. Now if the loop filters become slow because R is increased, what did we say happens at low frequency? It will go up by 20 log K, right? So that will be something like this at low frequency. Okay. So what do you think will happen at high frequency? It will go down. Why should it go down? So the area under above the 0 dB line, this is by Bode sensitivity, the area above the 0 dB line must be the same as the area below the 0 dB line. Clearly the area below the 0 dB line has reduced because the NTF has become less effective, alright. So by the same token the out of band gain must, the area above the 0 dB line must decrease, while the exact shape drawn in this picture may not be accurate, one can definitely conclude that the total area above the 0 dB line should decrease. Okay. On the other hand, if K becomes smaller than 1, what happens? The loop filter has become faster. In other words, the resistance has become smaller. Alright, so it's like increasing the gain of the integrator. Correct? So at low frequencies, the gain of the NTF will go down. The NTF will be better in band. Okay? And as we saw, better in band behavior can only be achieved at the expense of poorer out of band behavior. So it's probably doing something like this. Okay? This is pi by OSR. This is k greater than 1. This is k less than 1. This is k equal to 1. Does it make sense? Okay. So, extrapolating the same thing to higher order NTFs, what happens in practice is the following. So if this was the nominal NTF, all right. Please note that when compared to a first order modulator, this let's say this is third order modulator, what difference would you find? The slope will become higher and higher and higher for a high order modulator. For a first order modulator, this would probably do, the out of band gain of first order modulator is 2, alright. So it probably would do something like this, okay. As I go on increasing the order, this keeps falling, sharper and sharper and sharper, and which is why you are getting better and better in band noise performance. Is that clear? Alright. So, as I said, if the R's all increase, the gain becomes smaller, and this is what you will get in band. And okay, and if all the R's become all the resistors become too large, this is what you will get. If all the resistors become too small, this is what you will get. Okay. If you had let me ask you a question. If you had a third order modulator, if all the R's became, say, reduced by 10%, what can you say about the RMS value of the in-band quantization noise now when compared to earlier? So earlier there was some noise which is basically mod NTF the whole square d omega from 0 to pi by OSR. Alright. Now what has happened? The in-band value of the noise transfer function has fallen by how much? What is the in-band gain fallen by? All the R's reduced by 10%, so the loop gain has gone up by how many integrators are there in a third order NTF? There are 3 integrators, correct? Each integrator gain has gone up by 10%. So approximately the gain of the loop filter at low frequencies has gone up by 30%, right? 1.1 the whole cube. Does this make sense? No?
1 by 0.9 whole cube.
Yeah, 1 by 0.9 whole cube. 1 by 0.9 is 1.11. The whole cube is about 1.3, right? Okay, if you don't like it, it's 1.35. Alright? You understand? Okay? Is that clear? So even a 10% change, whereas for a first order NTF, a 10% change in the resistor will cause the low frequency gain to go up only by 10%. For a high order NTF, it will cause it to go up by whatever, n times 10%. Okay? Approximately n times, no? 1.1 whole to the power n is approximately 1 plus n times 0.1. No? Okay. Alright. So, what can you say about the in-band quantization noise. The in-band quantization noise is proportional to NTF whole square, right? So that is the integrated quantization noise. So the RMS noise will again be proportional to mod NTF. So the RMS quantization noise in band will go down by 30% if the resistors go down by 10% for a third order modulator. Does it make sense? So for high order modulators, what is the bottom line? Even a small change in the RC time constant can result in a large change in the in-band quantization noise. Does it make sense? Okay. So if there is a large change in the in-band quantization noise, what can you say about the out-of-band noise? There will correspondingly be, please note that we discussed, you cannot get good in-band behavior without losing at out-of-band frequencies. So if you got 30% reduction in the in-band quantization noise in the third order case, it must follow that the out-of-band stuff is going out of control by the area above the 0 dB line is increasing by 30%. Correct? So, and if the out-of-band gain is increasing, what can you say about the, can you make any comment about the stability of the modulator? The maximum stable amplitude, if you are lucky, will reduce. Sometimes the modulator will simply go unstable because the poles are going outside the unit circle. Does it make sense? Yes, sir.
We said area below the dB line is same as above, only for discrete filter.
No. Please note that the question is, this whole Bode sensitivity stuff is only valid for, we discussed it in the context of a discrete time system. But if I look at it like this, right, I am applying a discrete impulse here and what I get here is also a discrete impulse. That whole Z inverse by 1 minus Z inverse and all that is, basically this continuous time filter is nothing but, this is some kind of con job where you make sure that at the sampling instant the outputs are what you want, okay, at least in the nominal case. Alright. I mean, clearly the loop filter is the wrong loop filter when the RC time constants are no longer what you thought they were, okay, which is why we are interested in figuring out what happens to the modulator, right. I mean, if you just what do you call, if you shake the table and then the noise transfer function changes and the loop filter becomes unstable, I mean the whole loop becomes unstable, then this is not a viable technique, right, okay. But so, which is why you are interested in figuring out how much the RC time constants can change before the loop becomes unstable. Does it make sense? One way of understanding, so the bottom line is that do you think the stuff is more problematic when the RC time constants decrease or when the RC time constants increase? When the RC time constants decrease, the in-band performance goes down. So the out-of-band performance, the out-of-band area goes up. Okay, so it is likely all the time constants decreasing are, is probably the problematic case, the more problematic case. When all the resistors increase, you're not really, at least in such simple transfer functions, you're not very concerned, simply because all that you do is you take a hit in the in-band quantization noise, because if all the resistors go up by 10% in a third order loop, the in-band gain of the NTF will go up by 30%, which means that the RMS noise, quantization noise will also go up by 30%, but at least you have a stable modulator. You understand? So two things, one thing that we have certainly seen is that as the order increases, in-band noise decreases more, okay, for the same change in RC time constants. Alright. And as you know, even though you don't know, I am sure you will all believe me when I say, as you can't go on changing the RC time constants too far away from the original value of 1. Okay, if the RC time constants become too small, the modulator in all likelihood will go unstable. Okay. Now, given that fact, do you think the range over which the RC time constants can vary, alright, before the modulator becomes unstable, do you think that range will be larger as the order increases or smaller as the order increases? It will be smaller. And why? So clearly, from this discussion we see that if for a high order modulator, changing the RC time constants by a small amount is enough to change the in-band behavior by a large amount because of the number of integrators in the loop. Alright, okay, and we know that the in-band behavior and the out-of-band behavior are related. So a small change in the RC time constants would push the in-band gain much lower when the RC time constants become smaller. Okay, and the amount by which the NTF will go down in band will increase when the order is higher, which means that the out-of-band area will also go up much more when you have a higher order modulator. Okay, so clearly, you can easily drive the modulator into instability much more easily when you have a high order system and you vary the RC time constants a little bit. You understand? Yes.
In this particular case, we have just a plain integrator where it's 1 by Ks, where we can see it either as a gain change or the bandwidth change.
Yes.
In a higher order modulator, this will show up clearly as a bandwidth change and not as a gain change, because the gain will depend upon the components.
In a first order system, gain or bandwidth is the same thing.
Yeah, in a higher order system, will show up as the gain will show up as the ratio of components and hence should nominally remain the same.
No, that's not correct. The gain will be of the form 1 over RC, no? So 1 by S whole to the power n at low frequencies.
But we can also
Okay. Yes, sir.
If the out-of-band gain goes up by 30%, can we directly comment on the MS?
Well, at least from the discussion we have seen so far, it is the only thing I can say with certainty is that the maximum stable amplitude will reduce. Okay, I can't really. See, the Bode sensitivity integral is just giving you, a rough idea of what happens out of band. It is not telling you what the exact shape is out of band. That will depend on the details of the NTF you started off with and how you vary the, and so on. So at this point, the short answer is that it is not possible to comment on how much the maximum stable amplitude will change if the in-band gain reduces by some factor. Okay, so the aim of all this discussion is to give you intuition about what will happen, or what you can expect in practice. Okay, to get more visibility about the exact details, you have to actually do compute the stuff and figure out. Okay, and run sims. Okay, so this is what we saw will happen to the modulator if the R's all change. By the same token, if R's all were kept fixed and all the capacitors changed, you expect the same thing. Okay. So what do you suggest as a fix? No, the resistors are not what you want. So what do you do? If you are in the lab, what will you do? I'll remove this resistor, go look to the box and find the resistor I want and plug it in, right? So that you can't do that on an IC. So what you can do, however, is to realize a resistor, for example, as a combination of, for example, Alright. So this is R and this is delta R, delta R, delta R. These delta R's are all small resistors, and these are MOSFET switches which basically are controlled by some bits. Okay. Alright. And you can have, as many resistors as you like. And based on what the resistor values are, you can always go and tweak you can go and put in a digital code into the chip, which you set depending on what the resistor values are. Correct? So in this particular example, the resistance varies all the way from R to R plus 3 delta R, and you have to choose R and delta R intelligently to make sure that in spite of R varying by plus minus say 20 or 30%, okay, you should always be able to find some digital code which will bring the effective R back into a range which is acceptable for the modulator. Does this make sense?
Sir,
Yes, sir.
but we are not using resistors for changing convert output to current. We are using tech. We are using tech to convert voltage to current.
Yes.
We are not using resistors.
Correct.
So we should take care of that.
Correct. Absolutely. Yes. What he's pointing out is that if you use a current steering DAC, in this example we are assuming the output voltage of the DAC is a voltage, and we are converting to current using a resistor. Okay. So if you use the current steering DAC, then the unit element or the unit current source in that current steering DAC must also be dependent on R, because please note that we wanted that current source to be V by R. So if this R changes, you must be able to change that R also. That's and it's you can see that you replace every resistor by some kind of digitally programmable resistor, where once you know what the value of R is, the actual R that you have on the chip is, you can dial in a suitable correction code which will go and change the values of all resistors by the same factor. Is that clear? And as you understand, this is not the only way of changing a resistor value. One other way could be put conductances in parallel, or have some funky combination of series and parallel and all this other stuff. Okay, so the idea is just illustrative. Another way of doing this is to decide to change the capacitors instead. Alright, so you have the main capacitor, and then you have all these dummy capacitors, all these delta C's, not dummy rather. Okay, and this is again controlled by a digital word, and here the capacitance varies from C to C plus 3 delta C. Okay, or you can have a combination of various programmable R and programmable C. Okay, all right. The next thing is what happens when the op-amp is screwed up.
Sir?
Yes, sir.
Can these be auto-tuned?
Okay, so the other question is, okay, what we said now was, I'll somehow measure one resistor on a chip, and the way to do this is the following. I need to measure RC. Okay, now one way of doing it is to simply measure R, measure C of one capacitor you make on the IC. Okay, and we know that by the way the IC is made, all resistors and all capacitors will be off by the same factor. So once I measure one resistor and one capacitor, I know how far my RC time constant is from the required value, and I can go and set the right code. All right. So the question asked is there some way of automatically figuring out without having to spend time measuring the R and the C? So these such techniques are what are called automatic tuning techniques, right? Where you use there are many ways possible. For example, where you don't have to explicitly do it, you have a system on the chip which measures the R and C. Okay, And one key idea, one way of doing it is, for example, to pump a current I into a fixed current I into, let me see, okay, let me do another one. So let's say this current I is of the form Vref by R, alright, and this is C. What will this voltage be? It will be a ramp, okay, and what is the slope of the ramp? 1 by RC, okay, alright. So what I can do is sample the output. I mean, I reset the capacitor at t equal to 0, alright, and sample the output of this so I short this at t equal to 0. I sample the voltage across the capacitor at t equal to some m time periods, correct? I mean, you have a sampling clock. The whole continuous time sigma delta is working. The quantizer is being is working off of a sampling clock. So getting a clock is no big deal. It already exists. Okay. So you can sample the voltage across the capacitor at mt. Ideally, if the output should be mt divided by RC times Vref. The voltage across the capacitor is t by RC times Vref. Okay. So after time capital T, the voltage should be mt by RC times Vref. Okay. So you can measure this. Looking at this measurement, you will be able to figure out whether the RC is too low or too high, or is what you want. Okay. You can look at it, and then you go and once you know the value, I mean, that will give you, that's a measurement of the RC time constant. You can go and use that measurement to figure out what to do with the tuning bits of the programming bits of the digitally programmable resistors and capacitors. Is that clear? Okay. I mean, there are a bazillion ways of finding what RC are. Okay. One, all of them will have to involve some kind of dynamic measurement, because you are interested in measuring the time constant of the RC network. Okay. And there are another way of doing it is there are any number of RC oscillators. If you make an oscillator with R and C, okay, there are many ways of making oscillators where the frequency of oscillation is determined by the RC time constant, correct? And you can measure that frequency, compare it with the clock frequency, and then figure out if the frequency of oscillation is, if the RC time constant is too small or too large. You understand? So, and in any case, there are many variants of this technique. There are some techniques which exploit the fact that the way the quantization noise is shaped in the loop depends on RC. Okay. So, for example, if the in-band gain reduces, okay, what do you think will happen to the out-of-band gain? It will increase. So physically, what can you see looking into the waveform? So if the out-of-band gain increases, so the out-of-band, ideally you were expecting some kind of nice sine wave with some shaped noise, okay, some stuff like this. I'm sorry, I can't draw a nicer diagram. Okay. If the out-of-band gain becomes worse, what do you think will happen? The sine wave will be there, but the junk on the fuzz on top of the sine wave will increase. So, and this is all available digitally. Okay. I mean, the output of the ADC inside the quantizer will give you bits which are flipping, right? So, if the RC time constant becomes too small, then the flipping of the bits around the nominal value will be much more. Okay. And on the other hand, if the RC time constant becomes too large, the fuzz of the waveform around the nominal will become too small. Okay. So by looking at the fuzz, you can actually figure out if the RC time constants are correct, too fast or too slow, and you can apply the correction to the modulator. Okay. In any case, this RC time constants, I think lots of people are. I mean, this it's still a research area in the sense that a lot of people are trying to do it without having to do too much extra, without having to add too much extra hardware. Okay, so any technique like this basically adds some hardware. You need extra resistors, extra capacitors, some measurement, and all this other stuff. If something could be gotten directly from the sigma delta itself without having to do anything extra, then that would be a nice thing. Okay, so that's the all right. So yes, sir.
Sir, for the DAM, the gate current source, if it change, if it is constant and the resistance changes, then we are having the problem as you said, which is But if the tail current source itself is derived as well.
Yeah, that's what I said. So it has to the tail current has to be derived from as Vref by R. Okay. All right. So the last thing to consider in this thing is the Opamp non-ideality. The first non-ideality you can think of is basically finite DC gain. Correct. So what happens to if there is finite DC gain? Instead of having the integrator, instead of being of the form 1 over S, will be of the form, will become 1 over S plus 1 over A. Alright, the pole instead of being at the origin will shift into the left half plane. Okay, and you can see that as when I set S2 equal to 0, indeed the gain is A. Alright, now, so if I now, what do you think will happen to the noise transfer function? Intuitively, don't do the math. Can you tell me right away what will happen in the ideal case? The NTF will do this. Okay. Alright. Now with finite gain, what do you think will happen? Pardon? Gain will?
It will tend to flatten out in it. Flatten out.
So as S tends to 0, in the ideal case, you can see that the loop gain tends to infinity, right? Which is why the NTF goes to 0. Now, in the real case, when they have finite gain, what happens? The low frequency gain of the loop filter is limited to A. So the NTF cannot go below 1 over A. So what will happen in practice is that it will do this. Okay. So the in-band quantization noise will increase with respect to the case where the DC gain was infinite. You understand? Alright. Okay. I think we'll continue about the stuff tomorrow.